Okay, so let's go on to some basic definitions, and then we're going to play around with these and see if we can do some proofs and counterexamples. Okay. So first, we need to just define the different types of numbers we have. Okay. So what does it mean that n is even? This is true if and only if n equals 2k for some k within the integers. Okay. So that's n is even, n is odd. Say if and only if n equals 2k plus 1 for some k and c. Okay, so we got odd numbers, we got even numbers. Okay, that should be straightforward. Give everybody a second to write that down. Okay. So besides even and odd numbers, we also have prime numbers. Let's separate these out a little bit. N is prime if and only if for all positive integers say R and S, such that n equals R times S then R equals n and S equals 1. Oh, I'm off the screen a little bit, sorry. Okay. Or R equals 1 and S equals So basically, a number is prime if it's the only things that divides itself. It divides it is itself and 1. Okay. Now, prime numbers are very special numbers. Okay. The investigation of prime numbers, which we're going to do today in class, like trying to determine, well, can I prove that something actually is prime through a method of exhaustion, some other method? Or can I prove that something is not prime by factoring it into its prime factors? Because every integer can be created from its prime factors. Okay. Now, showing that primes are infinite is also another theorem. Oh, I didn't bring that one with me today. It's not that hard to prove that there are infinitely many prime numbers. You just assume that they're finite, and then you can show there's another one beyond that, and you have the rest of the prime numbers. But showing the placement of prime numbers within the number system is actually a very open question. Okay? That we know where all the primes are? Absolutely not. There are a lot of theorems out there that are not theorems, let's say conjectures, okay, hypotheses about where the prime numbers exist. The most famous of these is the Riemann Hypothesis, okay? So the Riemann Hypothesis, which was, Bernard Riemann came up with it in his dissertation, which is amazing that it was only 8 pages long. But Riemann said, and we might actually show you a video on the Riemann zeta function in class next time because it's related to infinite series, which are discrete sums, and the placement of prime numbers. And so Riemann said that all prime numbers, or all zeros in the zeta function, exist with a real part of 1/2 within the complex plane. So they all exist on one line in the complex plane with the real part being 1/2. Okay? And so no one has ever proved this. This is actually what is known as the Riemann Hypothesis. And if you can prove it, you get $1 million. There is a $1 million reward. Well, there's a $1 million reward from the Clay Math Institute that says if you can prove the Riemann Hypothesis, then we will give you $1 million. There are other theorems out there, I mean, not theorems, but so Riemann's hypothesis is what it is. But the one that has actually been proven from that Clay Math Institute is the Poincaré conjecture. So instead of a proof of something, Poincaré made a conjecture basically about topology and pulling strings into a finite spot. And so Poincaré made this conjecture in, I'm going to get the dates wrong, I think early 1900s. And it stayed around just as that, as a conjecture. And so actually, well, I'm not going to tell that story. But the Poincaré conjecture remained open for the longest amount of time. And then I believe it was also in the early 2000s, a mathematician in Russia was able to prove it through Ricci flow. And this was a big deal for the mathematics community. Strangely, the guy that proved it turned down the $1 million and stopped doing math, and now lives in the mountains of Russia with his mother. But so there are little quirks with mathematicians as well. So, okay, but all right, so let's continue with this. We'll start investigating primes here in a bit, but let's get through these definitions. So we also have something being composite. Okay? So now a composite number is basically the multiplication of two primes. Okay? Or not two, some. It is composite. I'll write this one like this. Say if and only if there exist positive integers R and S such that n equals R times S, and 1 is less than R, which is less than n, and 1 is less than S, which is less than n. Okay. We just have one last definition, and then we'll do some examples, okay? So we're going to actually switch this over just a little bit. So, we can say R is rational if and only if there exist, if it has to be positive, integers A and B such that R equals A divided by B and B cannot equal 0. So basically, rational numbers are anything that can be represented as a fraction. So infinite repeating decimals, yes, those can be represented as fractions. Okay? And something is irrational just if it's not rational. If it cannot be represented as a fraction, then it is irrational. Okay? All right. Let's do some disproving by counterexamples. Okay? And we're going to use these statements in our disproving by counterexamples and by actually proving a few things after that. Okay. So what do I mean by disproving by counterexample? Okay. So if you have a statement that you want to disprove, right? All right. So if you have the statement that for every x within the domain, if p of x then q of x. Okay? Now, if you want to disprove this statement, a counterexample is that there exists A and D, particular one, such that P of A is true and Q of A is not true. So in the formal symbols that we use, and so what is meant by those? This statement says that for every x in the domain, if P of x is true, then Q of x is true. Okay? To find a counterexample to that, all you need to do is find one example in the domain such that, yeah, P of A is true, but Q of A is not true. Okay, that's what's meant by a counterexample. So, okay, so let's try one. And I'll give you all a second to actually think about this. Let's just scoot up a little bit. And so I'm going to make this statement right here, okay? Isolate this. Say for every x in the integers, if 2m plus n is odd, okay, so now what is this? This statement right here, that's my P of x. Okay. All right, and then I need a then statement for my Q of x. Let's say then m and n Give everybody a second to write that down. And I want to give you all a second to think about this. Okay, can we think? All right, so what are we going to try to think about this? We're going to try to figure out two particular integers, m and n, such that if I do, well, 2 times n plus n, well, we get them to be odd. And we get the negation of this statement right here, meaning they are not both even. So we want to be odd and we want to be even. If they're both even, this whole thing ends up being even. So is there a way we can find something? If n is 0, now then the other one would just be 2 times an integer, hence making that it would have to be even. So that would not satisfy P of A. Because if you made n 0 and took this component away, then you would have 2 times an integer, and according to the definition of that, it would just be even. So that would actually be the negation of P of A. P of A would not be true, because it would be strictly even. Think about what if you tried combinations of maybe 1 and 2? How would I set that up? Okay. So let's think about it this. What if I said, okay, all right, we're trying to find this statement right here, okay? So if I let m equal 2 and n equal 1, okay? All right, so 2 plus 1, well, is up. Okay, so that's my then say and, we'll use the actual symbol, m and n are not both odd. Okay, now this statement right here is the negation of Q of A. Because m's 2, so m's obviously even. So that's what's meant by a counterexample. Can you find two subjects of the domain? Well, in this one there's two. Next one we're only going to have one. Such that it negates the truthfulness of that statement, hence being a counterexample. So that statement is not true. We prove that statement is not true because of this counterexample. Okay. I'm going to do one more counterexample, and then we'll do. When we get a little bit into the method of exhaustion, first we'll do a forward proof, and then we'll do some stuff involving primes. So, let's say for every x in Z, if P is prime, okay, so that's my P of x, then P squared minus 1 is even. Well, I didn't mean to go that far. That's Q of x. Okay. Now, if we start thinking about this, all right, with this problem right here, we need to find a certain prime such that P squared minus 1 is not even. Now, if you think about 5 is prime, okay? Well, 5 squared minus 1 is 24. That's even. 7's prime. Well, 7 squared is 49. 49 minus 1 is 48. That's also even. 11 squared is 121. 121 minus 1 is, that's even. So it's looking like this is actually true for a lot of them. But can anybody think of a prime number such that, well, yeah, it's prime, but if I do that prime number squared minus 1, I end up getting something that is odd. 2, yes, thank you. So, what we're going to do is let A equal 2. Now, 2 is prime. Okay? That would be P of A, and 2 squared minus 1 equals 3, and it is not even. And so that would be the negation of Q of A.